Welcome back to Physics 371 Online. Here, we'll introduce a new vector quantity which is related to the electric field and the electric polarization, and we call it, for historical reasons, the electric displacement, D. Let's summarize from what we've talked about so far. The effect of polarization on an insulating material is to induce two different types of effective charges. One is the volume bound charge density, rho sub b, inside the insulator, and the other is the surface bound charge density, sigma b, which is on the insulator's surface. So now let's put together the field due to all of the bound charge, which results from the polarization, and the field due to any other charges on the object. And these charges we will call the free charge, because they can be manipulated in the standard way using batteries and other kinds of devices. So, as we do this, inside the dielectric, or the insulator, we will write down the total volume charge density as rho sub b plus rho sub f. Again, the bound charge density plus the free charge density. From Gauss's law, we can write down del dot E is equal to rho over epsilon. But now we substitute for rho, realizing that we've got these two possible kinds of volume charges. When we solve and multiply both sides by epsilon 0, we can write epsilon 0 times the divergence of E is equal to, if we now substitute in for rho sub b, we know that that's negative del dot p. So we make that substitution here on the right-hand side. And now what we're going to do, in this expression, we see that there are two different divergences. So let's collect the divergence terms, remembering that in this expression now, E is always the total field that we want. So collecting the divergence terms gives us the divergence of epsilon naught E plus P. The plus sign comes about because it was negative on the other side of the equation. And this quantity, this divergence of epsilon naught E plus P, is equal to the free charge density. And so now, because this term in parentheses plays much the same role that the electric field did in the original version of Gauss's law, we're going to give this its own name. And here's where the electric displacement comes in. We're going to define the term in parentheses as D, the electric displacement. So if we do that, then our original expression coming from Gauss's law becomes del dot D is equal to rho free. Now this, as we can tell by looking at the equation we took this from, this ought to look familiar. Take a minute and remind yourself that del dot E was equal to rho. Del dot E was equal to rho, or epsilon 0. Now we have del dot D is equal to rho free. So it looks as though this is a special version of Gauss's law that applies to free charge in some kind of an insulating material. And that's exactly right. This new version of Gauss's law becomes, in differential form, exactly what we've written already. Del dot D is equal to rho free. But the integral form, which is actually most useful if we're trying to calculate the fields, will be just a little bit different. Remember that Gauss's law was the integral of E dot dA is equal to the total charge enclosed by the Gaussian surface divided by epsilon 0. In the integral form here, the only difference is that there will be no epsilon 0 because D has different units than E does. And so we can see that this will produce the integral of d dot dA, and on the right-hand side we'll have Q free enclosed. So it's the enclosed charge, but only the free charge. None of the bound charge is included on the right-hand side. And this clearly is going to take a little bit of practice to learn how to use. But the goal here now is, if we're given P, from which we can then calculate the surface bound charge and the volume bound charge, and if that gives us a high symmetry situation, then we can use this to find D. And if we know D and P, then we can get E directly, because those three are all related through the definition of D. So let me just take a few moments to go through a conceptual aside here. It's a little bit of a quibble I have with the way that D is normally defined in physics books. It's defined, and here I'll use the 3 bars to make that clear, it's defined as epsilon naught E plus P. But this is a little bit backwards conceptually, because if you think about it, E is the total field. P is the polarization field, the field that gets frozen in when the material gets polarized. And D functions really more like an applied field because it's due to external sources, something outside of the material itself. And so causally, if we think about what happens first, we apply an external field, right? And then the object gets polarized because of rearrangements of dipoles inside. And then, because of that effect, there's a net field inside the insulator, which is given by E. So causally, it would make more sense to solve for E, because it's the net field, and to see where it comes from. So E, then, shouldn't really be defined this way, but we could set E equal to D over epsilon 0 minus P over epsilon 0. And this makes more sense, at least to me. D represents the applied field. P represents then the field induced inside the object because of polarization, and E gives the net field. So here, schematically, here's what it looks like. Imagine we have a block of material, and we apply an external field E. E applied, right? Well, that's related directly to D, because if we look at the original equation, if there was no polarization, in other words, if there's no material here at all, and we just have a field in space, well, that field is simply going to be D divided by epsilon 0. And it also is shown in this equation. When there's no polarization, the second term on the right-hand side drops out. So D would simply be E times epsilon 0. So this E applied results in a D field, which is, of course, inside the material. But then that applied field causes a rearrangement of charge, and we know that that leads to a net positive surface charge on one side and a negative surface charge on the other side. All right? And it could also lead to a volume charge, but we're going to neglect that here because we assume these fields are uniform. So if that's the case, then the polarization vector, which always points from negative to positive, is introduced inside the material. And I've shown it to be shorter than D because the polarization effect always gives a field that's a little bit less than the applied field, never greater than. But the electric field that results from the polarization actually points opposite to P, right? Because due to these surface charges, a positive charge would feel a force away from positive and toward the negative. So the actual electric field associated with P would point to the left, and therefore the net field would be the sum of the two, which would be D minus the P vector, and that's the net field E. So that's just something that helps me to understand this equation better. The definition of D is straightforward, and that may be the easiest thing for you to remember, but just remember that conceptually D comes first, P results after that, and E is the net result of the two. And I will see you in class where we'll work some examples using this new version of Gauss's law.